Okay, so in this question, we are shown the top view of an assembly consisting of a carriage and a light rod BCT with small balls of mass M at either end, right? And then the carriage has a mass of 20 kgs and it's restricted to move in only the X direction, right? So it's guided by these two plates and it can only move in this direction, okay? And then at point C, the rod is mounted on top of the carriage, and then a motor is used to turn the rod. Cool. And then we asked, or we can assume that there's no friction in the motor, right? Then we're told that the rod will rotate above the guide rails. The balls each have a mass of 2.5 kgs, and we're given the distance r between the ball and point C. Then we're given the mass of the rod. The mass of the rod and the size of the balls can be neglected. We're told that the system starts at rest, and then a time-varying force F is applied to the left edge of the cart. So the force F is applied there, and it's time-varying, and it's basically given by this piecewise function. So it's 0 newtons when time is less than 0 seconds, and between 0 and 1 seconds, it's given by this function, and then when time is greater than 1, it's 0. And we're told that at time t equals 0, the motor is turned on. Cool, and it supplies a constant clockwise moment of 10 Newton meters. Cool, so we're asked to first calculate the acceleration of the carriage at time t equals 0 seconds. So to do that, we can use F is equal to ma. So we're given a specific time, so our force will know it from this equation here, right? At time t is equal to 0 seconds, we're looking at this equation over here. So that's in the interval t between 0 and 1, including the endpoints. So basically like that. So 0 is included. Okay, so our force is going to be equal to 100 times 1 minus 0, because t is equal to 0, which will equal to 100 newtons. Okay. Then we know that F is equal to the sum of forces is equal to m times he, where he is the acceleration of the center of mass. Okay, cool. So that's pretty much what we have to go off of from the formula sheet, right? If I can find the equation. So this equation here, that's all we have to go off of, right? Cool. Now we can find HE, which is just going to be equal to 100 divided by the total mass of the system, which is going to be 2.5 times 2 plus 20. So the mass of the balls times 2 plus the mass of the carriage, right? Cool, fine, we can get that. But then how do we know what the acceleration of A is, right? Because that's what we're looking for. We don't want the acceleration of G. Well, the acceleration of A is equal to the acceleration of G. Okay, so if you consider just the two balls, for example. So we're just dividing the system up into its separate components. So if you look at the two balls, so you have point C here, and you have that one and that one. The center of mass of this connection, BCD, the center of mass of this connection is going to be at C. So the balls are equidistant from point C. They're both a distance r away from C, and the balls have the same mass. So the center between those masses is C, right? And because the masses are the same, center of mass will be at C. Cool. Now, if we look at the carriage itself, right, we're not told anything, like we're not told that the mass is non-uniform or something. So we can also assume that its center of mass is going to be at point C. Cool. So if the center of mass of the entire system is at C and it's accelerating with a specific amount, then the carriage itself will be accelerating at that same amount. So if you were to think about it in velocity terms, the center of mass of the entire system, so this plus that, right, the center of mass of both of them, which will be at point C, is moving with a specific velocity in that direction, right? And then if you were to separate the two into their own separate components, the carriage will also be moving at that same velocity. I hope that kind of makes sense in a way. Yeah. I hope that makes sense. I really hope that makes sense. I guess another way of explaining it would be all these components are connected together, right? So the position of the center of mass doesn't change, right? And if you're saying that the center of mass moves with the velocity v, then the carriage has to basically keep up with the center of mass, right? So if you found the velocity of the center of mass, you found the velocity of the carriage. And same with the acceleration. The acceleration of the carriage has to kind of keep up with the acceleration of the center of mass. So they will be the same. Okay. I hope that kind of makes sense. So your acceleration at g will be equal to the acceleration of the carriage. Okay. Cool. Then for part B, we asked to calculate the velocity of the carriage at t is equal to 1 second. Okay. So at t is equal to 1 second, we have the force is still being applied, right? So yeah, and we can kind of look at it, since we're dealing with this force over here, we can kind of look at it as two states, right? But if you didn't see that right away, then it's okay, it's not a problem. So let's say you saw velocity and you thought, okay, chapter 5, let's try and use relative velocity. Let's try and do that and see what we'll get, I guess. So in order to use a relative velocity equation, we need to know the velocity of a point, right? We need to know the velocity of at least one point to use the relative velocity equations. And at t is equal to 1 second, we don't know the velocity of any point. So remember, this thing is accelerating, right? It's accelerating, and at t is equal to 1 second, it's going to have some velocity, and we don't know what that is. We don't know any velocity on any points at that point in time. Okay, so chapter 5 is out of the question. We can't use relative velocity, so you might be if you look at it as two states, so we're dealing with this equation here, and if we treat t is equal to 0 as state 1, right, and t is equal to 1 as state 2, then we can kind of work with that, and we could maybe use our energy equation, this T1 plus VG1, this equation here, could use that one, or we could use this equation, which is the change in linear momentum, or we could use the change in angular momentum. Okay, if you have two states, right? So if we go between 0 and 1, we could try and use the energy equation, right? But the problem is this u term over here. So this u term describes the work done by all the forces. So this force over here is doing work on the system. It's moving at a particular distance, but we don't know what that distance is. So immediately this whole equation becomes useless to us. Okay. The next thing we want to try is the conservation of linear momentum. Reason why, if you can use conservation of linear momentum, use it. Conservation of angular momentum is, well, for me it was kind of like a last resort kind of thing, just because it's a bit trickier to use than linear momentum. So conservation of linear momentum says that delta G is equal to the integral from T1 to T2 of the sum of forces dt. Cool. And the cool thing about linear momentum is that you can break it up into components. So this thing over here is a vector. It's going to have x and y components. So we can analyze the components that we want, right? And also another thing, so G, you'll see from your formula sheet that G is equal to the mass times Vg. Okay, so G is equal to the mass times Vg. Okay, now let's think about, because we can divide this into like two components. We can either do x, we can do y. We need to then choose which axis we're going to follow, right? We can either follow the y-axis or follow the x-axis. And that's going to depend on what component of velocity you want to look at. So if you think about this thing moving, it's only going to move with an x velocity. It's not going to move in the y direction, right? So we're only going to consider delta G in the x direction. So we can write this as delta G in the x direction is equal to the integral from T1 to T2 of the sum of forces in the x direction dt. Cool. So now we go back and look at our diagram, and we look at all the forces that act in the x direction, and this is the only force that acts in the x direction, and between times 0 and 1 it's given as this equation here. So our delta Gx is going to be equal to the integral from 0 to 1 of 100 multiplied by 1 is a plus or minus t dt. okay, which is going to be equal to 100t minus 100 over 2 t squared evaluated from 0 to 1, which is going to be equal to 50. Okay, and that's delta gx. Okay, cool. So now we've got an equation for delta gx. Now we want to write it in terms of velocity. So delta gx is just equal to the total mass times vg2, which is our final in the x direction, minus m times vg1 in the x direction. Okay, and we're told that the system starts at rest, right, before the time varying force is applied. So at t is equal to 0, the system is at rest, right? So there isn't any velocity in the x direction at t is equal to 0, so that term falls away. And then we're just left with this term over here. So m vg2 in the x direction is equal to 50. So vg2 in the x direction is equal to 50 divided by the mass, which is going to be, was it 2.5? It's going to be 2.5 times 2, which is the mass of the balls, plus 20, which is the mass of the carriage. Cool. And then remember our observation from before. We found Vg, and we can say that Vg is equal to Va, the velocity, of the cards itself. Cool. Then we're asked to calculate the angular velocity omega of the rod BCD at t is equal to 2 seconds. So at t is equal to 2 seconds, the force is 0. Okay. Yeah, so the force is 0. We aren't given anything else. We also know that the moment, it's constant and it's equal to 10, right? So in essence, because this moment is continuously being applied, it's a constant moment, but that's going to cause this to spin faster and faster. As time goes, this rod is just going to keep spinning faster and faster, right? So the moment contributes to the angular acceleration of BCD, and if a constant angular acceleration is applied, then you're going to get an increasing angular velocity. I hope that kind of makes sense. So, cool. If we were to if we were to apply the moment for a while, so 2 seconds, then it will go from 0 to some angular velocity at the time t is equal to 2 seconds. Hope that kind of makes sense. So let's try and go through the whole process again. So we'll start with chapter 5 stuff. We're given a moment, right? And we don't have the velocity of a point at t is equal to 2 seconds. So can't use relative velocity in that case, right? So chapter 5 is out. In terms of chapter 4, can we use the energy equation? At t is equal to 2, we don't have this force over here, but we do have this moment acting on the system, right? And we don't really know what the work done would be, right? So, okay, we don't really know what the work done would be. And then, the last, okay, we can also check linear momentum. If you check linear momentum, the change in the linear momentum, we're just going to get 0. And remember, linear momentum relates to velocity, the linear velocity, not the angular velocity. So you won't get an answer for that. You won't get an answer for the angular velocity of BCD. Okay, so from there we can see that we have to apply conservation of angular momentum. Okay, so conservation of angular momentum tells us, conservation of angular momentum, so I'm just going to say HO, where O is some fixed point, is equal to T1, T2 of the sum of moments at point O dt. Okay, so literally the same as the linear momentum one, right? Cool. So this will then, I'm going to do it about point G, right? It's going to be equal to the integral from T1 to T2, the sum of moments at G dt. So the reason why I'm doing it at point G, or the center of mass, is because that's where my moment is acting. So I know the sum of moments at that point. If I were to do it at another point, then I'd have to then go and calculate the sum of moments at that point. Right. Yeah. So rather do it here at point C, which is the same as point G. And the reason why I'm going to label it as G is because it helps me identify which equation I need to use. So I know if it's at point G, then I'm going to use this equation for my angular momentum, where it's going to be, I can either use this, where it's rho times, which is, so this rho I is the relative distance between a particle and the center of mass. So for example, this particle over here, the distance of this point D to the center of mass is going to be R, whatever R is. So that R as a position vector would be this rho I. And then this rho I dot is the relative velocity of this mass to the center of gravity. So we can do a relative velocity equation where we say VI is equal to VG plus VI relative to G. This VI relative to G is that rho I dot. Okay, I hope that makes sense. Cool. So we're asked to calculate the angular velocity omega at t is equal to 2 seconds. And we're going to use conservation of angular momentum. Cool. So we're going to pick a time 1. So we're going to pick it at 0 seconds because we have information about the moment at that point in time. So we know that from time t is equal to 0 seconds, the motor is turned on and it supplies a constant clockwise moment of that much. Right, so delta Hg is going to be equal to the integral from 0 to 2 of 10 dt, right, which is going to be equal to 10t evaluated from 0 to 2, which is going to be equal to 20. Okay, cool. Then what we want is to find our delta Hg, right? So delta Hg is just going to be equal to Hg2 minus Hg1, right? And then Hg2, let's start with Hg1, right? Hg1 is going to be equal to the sum of rho I crossed with, so I'm writing this equation here, crossed with mi rho I dot. Okay, so you might be asking, when do I use which one? So this, remember, this is just the relative velocity, the velocity of the particle relative to g, and this is the absolute velocity, so it's the velocity of the point itself, right? So this term over here breaks down to it breaks down to v, okay, so vi, right, which is that, is equal to the velocity of g plus v I relative to g, right? So you're going to have to keep adding Vg, keep adding Vg, keep adding Vg. And sometimes you don't really know what Vg is, or you just don't want to calculate it. So a lot of the times, this is the easier equation to go for. But if you're provided with the absolute velocity of the point, then rather use this equation. But most of the times you're going to be using this one. Okay, I hope that makes sense. So cool. For state 1, velocity is 0, right? It's all stationary. So this rho I dot is going to be 0, so everything becomes 0, right? And then for Hg2, we're going to use the same equation times mi rho I dot, right? And then this is going to become r crossed with mi times this relative velocity. So it's the velocity relative to point G, right? And the velocity relative to G is just going to be omega, what was that? Omega BCD. Omega BCD crossed with R BCD. Not R BCD, sorry. Just R. This R here. So that one there. Yeah, hope that makes sense. Cool. Then you add the two together, so it's going to be the sum, right, from the two thingies. So for this particle D, and for particle B. Cool. Okay, then once you've calculated that, you'll equate it to this 20 over here, right? So to write everything out again, just so that it makes more sense, we're going to have delta Hg, which we said was Hg2 minus Hg1. We said that Hg1 is 0 because it starts at rest. And then delta Hg is going to be equal to this over here. So it's going to be equal to R times Mi times omega BCD times R, right? And then the sum of the two. And in actuality, you can literally do the scalar multiplication of this, and you can multiply it by 2. Reason why is because angular momentum is kind of like a moment in that it creates a vector that acts out the page, right? So the angular momentum caused by this particle is the same as the angular momentum caused by that particle. But if you're uncomfortable with that, or you're not super confident, I'd recommend you do the whole vector thingy, right? Okay, so I'm just going to write it like that, and then we know that delta Hg is equal to 20, right? And then you just solve for omega BCD from that. So we know that, yeah, then you just solve for omega BCD. Cool, hope that makes sense. Then part D, calculate the work done by the motor between t is equal to 2 seconds and t is equal to 4 seconds. Okay. So in this case, we're asked to calculate the work done. So U12, right? And there isn't a change in, gravitational potential energy. So it's not moving up or down or whatever, it's just moving along a straight path. So there isn't change in gravitational potential energy, there's no change in elastic energy, there's no spring or whatever. So this will be equal to T, to basically the change in T, change in kinetic energy, right? Cool. And then if you look at this equation, kinetic energy is equal to a half times mi vi squared, right? So the sum of the kinetic energies of all the particles, right? Or it's equal to a half times m times vg plus a half times mi rho I dot squared. So this is basically the kinetic energy of the system with using the velocity of the center of mass plus the kinetic energy of the system using velocity relative to the center of mass, right? Okay, and then let's try and go through the question and see what happens at time is equal to 2 seconds and time is equal to 4 seconds. Okay. Okay. We aren't really given any info on that, I guess. So what I want to try and do, let's get the memo and see what they did. Okay. So, we know that the only external work is going to be from the motor, right? So, because this force is 0, the only work done is going to be from the motor. And, yep, he wrote the correct equation over there. Okay. And then, cool. Okay, so they're basically saying that the system is sort of at rest. So the thing isn't moving this way anymore. Kind of sucks that they didn't say anything about that, but it's not moving this way anymore. It's just only the rod BCD is going to be rotating. Okay, so your kinetic energy will be from the rotation of BCD, right? The carriage itself isn't moving anymore, right? So the carriage won't contribute anything to the to the kinetic energy. Okay, hope that makes sense. Where's that? Okay, cool. So we can use one of two equations. We could either use the individual one. Okay, I don't know what happened, but we could use that one that says it's equal to the sum of all the kinetic energies of all the different particles. So sum of mi vi squared, right? And then if you look at the velocity of vi, we can relate it to point C. So remember, I is each of these particles, point D, point B, right? Okay, so let's do point B. So velocity of B is equal to v C plus vB relative to C. And we assume that at t is equal to 2 seconds, vc is equal to 0, right? So that's 0. And then so that's 0. Then vb is going to be equal to omega bcd, right? So omega of this thing, right, multiplied by r. Okay, cool. So that's what vp will be equal to, and you'll find that thingy will also be the same thing. The velocity of the other point will be the same thing. So vd is equal to vc plus vd relative to c, and vd is equal to omega bcd cross with r. Okay, cool. So from there we can plug this in here and we'll get the kinetic energy, right? So we need the kinetic energy from t equal to 2 seconds, and then T equal to 4, which was our final, minus the kinetic energy from T equal to 2 seconds. Okay, so we can plug this in to get the kinetic energy at T equal to 2 seconds, but our problem is that we don't know what omega PCT will be equal to at T equal to 4 seconds. So remember in the previous question, we found what it would be at T equal to 2 seconds, right? So we'd have to go through that whole thing again where we find delta H, and then it will be equal to the integral from 0 to 4 now of the sum of moments. Okay, dt, which is going to be equal to integral from 0 to 4 of, what was it? Was it 20? 10 dt, which will be equal to 40. Okay. Then this delta Hg, we said was equal to 2 times, what was that equation? We said it was equal to this, 2 times R times Mi, so the mass of each ball, times omega BCT times R again, right? And that will be equal to 40. Then you can solve for WPCT. I'm just going to call this 2 for like state 2, right? Then we do the same thing, right? And we basically will substitute that here into this equation to find Vd at state 2 and Vb at state 2. Okay, so then U12 will become the sum of kinetic energies of each particle. So it will become for state 4, it's going to be the sum of Mi, and then it's going to be omega PCD 2 for state 2 crossed with R squared. So that's our velocity squared, right? So this is 4 at T equal 4 minus the sum of Mi omega BCD state 1 times R squared. Okay, and then that will give you your the work done. Okay, I hope that makes sense, and yeah, good luck with the test tomorrow.